Erin and then Hugh. So Erin is talking about summer sea ice variability from a novel proxy. Okay, thank you.
Yeah, thank you for the introduction. Two things to say before I begin. First, a big thank you to the team behind this presentation. As you can see, we're a large group based at Durham and British Antarctic Survey. And second, an apology that I'm going to talk about regurgitated seabird stomach oils ahead of your lunch break, but it's actually better to have it before than after. So yeah, I'd like to introduce our project looking at summer sea ice variability over long time scales. And just to introduce you to this weird and wonderful archive, we are relying on these beautiful Antarctic seabirds, the snow petrels, as our new indicator for past sea ice variability. So the way that this approach works is that the snow petrels have a very close association with the sea ice. So they forage at the sea ice edge or within the sea ice pack and create these stomach oils which record a record of their diet. How this works for our project is that during the spring and summer, they then are nesting on land on the Antarctic continent. And here they are regurgitating their oils, often as a defense mechanism. And hopefully you can see this lovely build-up in front of the nesting site. And that is containing a record of both the diet and also the environmental conditions within the sea ice where they're foraging. So yeah, if you cut one of these open, we actually see this really beautiful record, beautiful lamination. It kind of looks like a tree ring record. It does not smell like a tree ring record. But we're then using this as a kind of a history of snow petrel diet. There are lots of ways that we're addressing these archives in the project that I want to introduce you to today, which is called ANTSI. Today I'm going to focus on some records here from the Dronning Maudland region. So we have deposits extending from the Sauron Mountains right through Dronning Maudland and down to the Theron Mountains. We have more than 80 deposits that we're working on, which extend from the present day right back to more than 50,000 years ago. And we're doing multi-proxy analysis on these records to really try and tease apart what's been happening to snow petrel diet through time. You can hopefully see these kind of colored shaded semicircles on here. That color coding reflects the breeding site where we're collecting the deposits, and the circle is showing you how far from the breeding site the snow petrels will tend to forage. So from this you can see that they are integrating information over a relatively large area of the sea ice environment, but at the same time they're relatively constrained to the Antarctic coastline. So today I just want to focus on some of our new data from these sites, first of all just linking diet to sea ice. But before I do that, I would just want to pause to talk about how we're doing some ground truthing work, which is trying to understand in more detail how snow petrels interact with the sea ice today. And we have been fitting GPS trackers to the back of snow petrels, identifying where they've been foraging, and then subsampling a whole suite of dietary samples so we can make this biochemical link between the foraging and what we find in the deposit. So just as an example of some of that data, this map is showing you the distributions of snow petrels that we tracked here just from the Sauron Mountains and then also from Svartamaren to the west. And hopefully you can see in the background we have the January sea ice extent here and the February sea ice extent. And we're seeing that the snow petrels are indeed foraging within a sea ice influenced environment. And they're also being relatively constrained to the coastline. What we're also seeing, which may not be clear here, is that sometimes they are extending beyond the sea ice edge and showing some flexibility in their foraging behavior. But I say that with the caveat that we were tracking a sea ice-associated seabird in a time of very little Antarctic sea ice. So we have new data now from different field seasons as well to try and understand how local this impact is. But what we're hoping to contribute to this research community is also to provide this link between all those ice core records which are integrating sea ice and climate over a wide area with also the marine sediment evidence from further offshore, which has a lot of information about sea ice extent. Okay, for some of the data, I just want to present the dietary information that we're using today and show you some examples of how we're reconstructing centennial and millennial scale variability. And the way that I'll do this today is just to focus on two sets of indicators and trying to use the diet as an indicator of change. So we use the presence of copper and particular distributions of fatty acids to say something about the presence of Antarctic krill. And then we're using different distributions of fatty acids and a reduced abundance of copper to identify times where there's more fish in the diet. The reason why we are looking at these two end members is that today, when the snow petrels are foraging beyond the continental shelf edge, we see an enhanced contribution to krill in the diet. When they're restricted to the continental shelf, we see a much higher increase of fish. And all of the data I'm going to show you is sitting on radiocarbon timescales. Okay, so as I said, we have more than 80 deposits. I just want to flag here, these are subsections through a small number of them, just to flag that we have lots of overlapping sequences, complementary sequences, extending over different time windows. So we're using this to build a really rich data set about changes through time. So just to highlight some data here, this is from the Theron Mountains for the very latest part of the Holocene. We have 3 deposits here, and I'm showing you the copper to aluminium ratios here as an indicator of copper input and krill input, and then some fatty acid distributions, again, reflecting Antarctic krill. The way that these proxies are developed is they're not showing exactly the same link to the diet, so we don't expect the long-term variability to be the same. But hopefully, I can convince you that there's some variability here where we see highs and lows in krill contribution to the diet, which is reflected in multiple proxies and at multiple sites. Some of them are synchronous and some of them are not, and we're continuing to work on that data. What was interesting for us, though, is to pick out this millennial scale variability in diet, even during the last 3,000 years. And when we compare that to the Dronning-Maudland epoch temperature data, we're starting to see that that millennial scale variability in ice core temperature might also be reflected in changes in the sea ice and the diet of the snow petrels. So our interpretation here is that there's fluctuations in foraging between the continental shelf and offshore, which might reflect a sea ice margin migrating on millennial timescales. And then we can also push this kind of data further back in time. So I just want to show you an example of some work that we published last year in Climate of the Past, looking at this deposit from the Untersee Oasis. And this deposit spans the interval where Antarctic sea ice extent was at its maximum ahead of the last glacial maximum. So I won't show you all the wiggly lines. Not everyone likes them as much as I do. So this is just a summary of the deposit. A mixed diet at the top, fish in the middle, mixed diet at the bottom. So we're also seeing that variability in diet and variability in foraging location. So we could interpret this as fluctuations in the sea ice margin. That's one approach, as we have done for the Holocene. But on this map, hopefully you can see that here's our site. Here's where the marine sediment data tells us that the sea ice edge was located, and it's way beyond the snow petrel foraging range today. So instead, what we think must be happening here is openings in the sea ice, so polynyas developing, which are then giving the snow petrels somewhere to feed because they need open water to access their prey. So this idea of polynyas opening the sea ice pack is not new because these sediment cores here are showing where polynyas during the LGM have been suggested. But what we think is interesting here is that this fluctuation in diet might be telling us that the polynyas have been shifting from being over the continental shelf to further offshore. And for this audience, we think that could also be telling us something about fluctuations in continental shelf availability. The snow petrels can't feed in a continental shelf setting if the ice sheet is at the continental shelf edge. So as well as thinking about kind of changes in vertical ice sheet extent, we might also be able to say something about the lateral extent. So with that, I'll summarize just by saying that I hope I've convinced you that we can reconstruct changes in snow petrel diet over time, that we're now starting to develop information about centennial and millennial scale variability in sea ice extent, And it'd be really interesting at this meeting to discuss also how we can pull that information together with those of you working on changes in sea ice and Antarctic climate over time. Thank you.
Thank you for introducing me to a new archive that I've never heard about. Are there any questions in the room? Okay, probably that was too much before lunch.
There's this one.
Thank you very much for the talk. So, if I understand well, you relate the deposit to the change in sea ice. Is it possible it's also a change in the ecosystem functioning, that the krill is going away because there is nothing to eat or for them, or the fish go away and then they just choose something else, even if the physical setting remains the same, but the biological or the availability of prey is not controlled by the physics but by something else? It's possible, or is it something which is ruled out?
So it's possible, but maybe that's possibly on a finer scale than the integration of the information that we have from the foraging, because we're integrating over potentially several hundred kilometers. So I think within that zone, there should be the availability of the prey, unless perhaps the sea ice conditions are limiting access to that. But what we're doing at the moment is Louise Syme has been doing sea ice modeling work, and we're putting that into ecosystem model to also predict where the prey should be to test against the deposit data. So I think that will hopefully address that question. If the model predicts there should be no krill and we find it, then there's something that we can comment on.
Okay, thank you.
We've got time for another question if there is one, but if not, we're moving on to the next speaker, who you've already seen. Hugh Horgan.